This is video 1.11, evaluating measurements. Our first objective is to define and distinguish between accuracy and precision.
And we want you to indicate if a given set of measurements is precise, is accurate, is both precise and accurate, or is not precise nor accurate.
And lastly, calculate the percent error of an experimental result. This is from reading chapter 2.7, starting on page 51.
Let's get down to it. So when we talk about accuracy in science, what we're referring to is how close a measurement that you make in a laboratory or a set of measurements you make in the laboratory are to what's the true or accepted value of that measurement. So a lot of times we'll use that kind of target analogy here. So if the bullseye at the center of the target is sort of the standard or the accepted value, what we're looking at is the grouping around the bullseye. So anything where the center of your group is around the bullseye is accurate. So if we had, let's say we took 3 shots at the target and we hit here, here, and here. Let me make those a little bit bigger. Okay. So none of those is exactly right on target, but kind of the average of those would be right in the middle. So that would be an accurate group by this definition. Same thing, actually. Now, if you made 3 shots that were, let's say, super close to each other,
but far away from the center.
So that would not be an accurate group of shots there. That is, the accuracy is off. Now you might say, well, but this is a better grouping than this one. Well, we haven't talked about precision yet, which is the next topic, and you'll see how they relate in a second. But let's look at some actual lab data here then. So let's say students calculated the density of iron 3 different times, or 3 different groups of students calculated the density of iron. One group found 7.7 grams per milliliter, one found 8.1 grams per milliliter, one found 7.9 grams per milliliter. And the accepted density is 7.9.
Yep.
Is that an accurate group of measurements?
Well, I took them all up, added them together, and found their average. And I found the average to be 7.9 of those 3 measurements. So I would say, yes, they're very accurate.
Okay, so the average, not only one of the 3 was exactly 7.9. One was a little bit lower, one was a little bit higher, but the average is right on the money. So that's an accurate group of measurements.
All right, so the next one is precision. This is how close the values of a set of the measurements are to each other. So unlike accuracy, where you want to be at the bullseye or average to the bullseye, precision is all about how close you can put these. So an example of good precision would be any close grouping together. So I'm going to take some points, and you have them closely grouped. That would be a precise grouping. But if you had a shot here, 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 and here, they're nowhere near each other, so they would not be precise, but in reality they might be accurate if you averaged them together. But those are 2 different things you have to look at. So remember, closely grouped would be precise. So we want to look at an actual example. We have 3 different students measuring the mass of a metal cylinder. Their values were as follows: 112, 111, and 110. The actual mass of the cylinder was determined to be 100. Are the measurements precise? Are they accurate? So 112, 111, 110, the way we decide if something is closely grouped is if it is a small percentage of the total off of from each other. That was how we would decide. So they're all off by each other by 1. So that is a very small amount of 100. So since they're off by a small percentage of each other, I would say those are precise. Now, if it was like 15 apart or 20 apart, I would no longer call that precise, because if you are 15 or 20 grams off when your total measurement's 100, that's 20% of the total mass, and that's a big difference between each measurement. So if it's a small percentage, like 1 or 2 or 3%, then you could say, yeah, that's precise, but we eyeball that for the most part.
Yeah, there is mathematical things to do it, but we don't get into that in here. Another thing that you can do is just look at where's the first place the measurements are different. And you can see that they're only different at the very last place value of the measurement, so that's a pretty good indicator that they're precise. They're agreeing at all the earlier place values.
So precise, yes. Accurate, no, because it's off by a good 10 or 12. So I'm going to say accuracy is no.
on
this one, so they are precise, but probably not
Now,
accurate.
what would that indicate to us as chemistry chemists? If we're getting a group of measurements that agree closely with each other, but they're way off from the standard.
Either you are performing the same thing the same wrong way all 3 times, or you have something wrong with the instrument you were using. We will actually cover that, I think, in the next slide.
Okay.
So drawn here are 4 different examples of things. Yes, we actually would like you to copy this so you have a nice pictorial representation of what these things mean. So we're going to remove away one of these boxes, and we're going to see the word precise. So as we just defined, precise means things are closely grouped. So looking at this first box, looking at this first box right here, all those are closely grouped. Do you agree with that?
I would totally agree with that.
And would you agree with this other set being closely grouped?
Absolutely.
Okay, so the precision is both correct.
So they're both precise. Now let's look at the bottom two. So now we're asking about, now we're saying these are imprecise. Why are they imprecise? Because neither group is particularly
Close together.
close to one another. Okay, they're spread out
Okay.
a little more.
So this next box that we are going to remove is going to uncover a new thing. Let's try to predict what we think this one is now. So this is precision and this is imprecision. What do we think might be behind this black box if they're all centered around the center?
I'm going to say that's going to be accurate.
I'm going to say that's accurate. We are correct. So in both cases, this one is accurate because they're all closely grouped and they would average to about the right answer. These ones, while being imprecise, are still accurate because, well, they average.
The center of the group is right at what the accepted value is supposed to be.
And that would be a reproducible error going on here. So let's predict this next one. So these are still precise. These ones are imprecise. So what do we think is behind this box?
I'm going to say not accurate or
inaccurate. All right. Okay. So this is where we kind of talked about in the last slide a little bit about this systematic error. Systematic errors occur when you do something incorrectly to take a measurement multiple times, or if the equipment that you are using has something flawed that causes it to give you reproducible numbers that are just wrong.
Like, for example, your thermometer, the calibration could be off on it.
Yep.
So you're getting the same temperature every time, but it's always 3 degrees off of what it's supposed to be.
Yep. So you can see here, this one is precise but not accurate, and this one is imprecise and not accurate. So this guy was just out of luck when he was taking his time putting those X's there.
So lastly, we're going to look at percent error. This is the mathematical way that we do evaluate the accuracy of laboratory results. So a lot of times we're calculating the density of something or the melting point temperature of something, and we get this laboratory or experimental value, and then we compare it to what the accepted value is, and we can do a calculation to see kind of how accurate we were with our result. So there's a simple equation we do. If we want to find the percent error, we're going to take the difference between the experimental value, that's the value that you got in the lab, from the accepted value, subtracted away from that. The accepted value would be what a textbook says it's supposed to be. The density of iron is supposed to be, something, or the density of aluminum. And then you take that difference and you divide it by the accepted value and multiply by 100. So the closer you are, the smaller the percent error comes out.
And really, the plus or minus that you're going to get is going to tell you how you are off. If it's a positive, that means you are over the value. If you're negative, that means you're under the true value. So let's take a quick look at an example. We have John. He found the density of a block of aluminum to be 2.8 grams per milliliter. The accepted density of the aluminum was 2.7. So what is his percent error?
So it's going to be 2.8 minus 2.7. Put that in parentheses, so we do that first, and then we divide by the accepted value, which is 2.7, and then we multiply it by 100 to make the answer come out a percentage, and so I've got 3.7% error.
Remember to use proper significant figures.
And
they give you
positive.
2.7. Yep. So we know he had over slightly the value that he should have had.
Go ahead.
Now, this is what we use a lot in our labs. We do the percent error a lot. We expect you to be able to perform this math. We will help you out with this as well on our labs as well.
All right, so for your post-video questions, we've got 3 questions based on the information. In the first one, we want you to draw yourself a target there and show a series of hits on the target. I don't know, maybe 4 or 5 hits, which are precise but not accurate.
Yep.
Okay, and then the second one, you can read it yourself and just comment on whether the group of measurements is accurate and whether it is precise compared to the accepted value. This would be your accepted value, 10.00 centimeters.
Good call.
And then the third one, we want you to calculate the average length from number 2 above and find the percent error.
All right. Good luck. Talk about it tomorrow.